In this lecture, we focus on a special type of AC circuit that has what's called resonance in the circuit. And we're going to focus on series resonance for this case. So a very simple series resonant circuit has some type of an AC source, and that source has some frequency associated with it. And there's also an inductor and a capacitor in the circuit, and also possibly a resistor. There's always some amount of resistance in the circuit, so we'll focus on a situation where there's also going to be some resistance. So you'll notice that the frequency here is not written down, right? So there's no specific values given for any of these, and then the frequency is sort of like, opened. And so let's focus on a special case of series resonance where what happens is that you can set this frequency in the circuit to be such that the reactance for the inductor is exactly equal to the reactance for the capacitor. And because these are out of phase with one another, those two impedance values completely cancel each other out. So if you think about your general knowledge of physics, resonance occurs when you match the natural frequency of oscillation for something with some outside frequency, right? So like a tuning fork, for example. Like if you were to strike a tuning fork, it vibrates at a particular frequency. And so you're causing it to vibrate at its natural frequency of vibration. So resonance occurs when you cause an object to vibrate at its natural frequency of vibration. So even in a circuit like this, there is a natural frequency of vibration, and if we can match that natural frequency, we can actually get the maximum amount of power out of that circuit. And specifically, of course, real power. So at resonance, we get the maximum amount of power through that particular resistor. And so that's what we're going to focus on. So I can write down what the impedance values are for all of these different components. So I have a resistor in the circuit, so I have the resistance or the impedance of the resistor. I have an inductor in the circuit, so it has some impedance and some inductive reactance. And then I have my capacitor in the circuit, and so it has capacitive reactance, phase angle of -90. So this is a series circuit, so the total equivalent impedance in this circuit is the resistive piece and then adding the inductive and the capacitive pieces together. Keeping in mind that I can find the reactive components for each, the inductor and the capacitor, by using the natural or the frequency, the angular frequency times the inductance for an inductor, and the angular frequency is 2 pi times the frequency, the actual frequency in hertz. And then I can do the same thing for the capacitive reactance. It would be 1 over the angular frequency times the capacitance, which is, of course, 2 pi frequency times the capacitance. So I can write down what those reactive components are. If I go ahead and I substitute those reactive components in, I get that the total impedance in a series circuit that has a resistor, an inductor, and a capacitor can be written in terms of the inductive value, capacitive value, and the angular frequency in this particular way. So resonance is going to occur when the frequency in the circuit is such that we are going to have the maximum power dissipated by the resistor, the real power. And so if we can adjust the frequency of the source until we get that maximum power in the circuit here, then we've reached resonance. And that resonance frequency, or that frequency that we find, is called the resonance frequency. And so we've written it as F with a subscript R. I think a little later we put that as a subscript S because this is a series resonance circuit. So the maximum power is going to occur in the circuit when I have the maximum current, right? So power in general through that resistor is the current squared times the resistance. And again, these are just the amplitudes of those particular components. So what is the amplitude of the current squared? And when the current is a maximum, you will get the maximum power. So the current is going to be a maximum in this circuit when the overall impedance in this circuit is a minimum, right? So because the current is the voltage divided by the impedance, when the impedance is small, the current is large. We just said that the total impedance in this particular circuit is just the resistive piece plus the combination of the inductive and the capacitive pieces. And this is going to be a minimum value. This impedance value is going to be a minimum value when the reactive inductance is exactly equal to the capacitive inductance, capacitive reactance, right? So when the two reactance values for the inductor and the capacitor are exactly equal to one another, because if they're equal to one another, it's going to cancel out this part of the impedance, and the only thing that you have is the resistive piece. And that's when it's going to be a minimum value for that impedance. Any other time that you have some value in here, then when you find the total impedance, you take the square root of the resistance squared plus this component squared, and so you're going to have a bigger value. So the overall minimum impedance is all resistive, canceling out those other two components. So let's see if we can figure out what that resonance frequency is when the reactive inductance is equal to the capacitive reactance, right? Inductive reactance is equal to the capacitive reactance. So if we set those two equal to each other, and then we put in that the inductive reactance is the angular frequency times the inductance, and the capacitive reactance is 1 over the angular frequency times the capacitance, I can cross multiply, right? I can bring this angular frequency up here, the inductance down here, and I get that the angular frequency squared is equal to 1 over the inductance times the capacitance. And if I take the square root of both sides, I get that the series resonance frequency, this is the angular frequency, is 1 over the square root of the inductance times the capacitance. And then I can figure out the actual frequency in hertz by taking the angular frequency and dividing by 2 pi. And so I get an expression for what that frequency would have to be. So the idea here is that if you had a circuit that had an inductor, a capacitor, and a resistor in it, you could adjust the frequency of the source until that frequency exactly matched this particular value, 1 over 2 pi square root of LC. And once it reached that particular frequency, the two inductive reactance and capacitive reactance components would cancel each other out, and you would have the maximum amount of current passing through that circuit, because those two impedance components would cancel each other out for the inductor and the capacitor, and you would only have resistance in the circuit. So essentially you're tuning your circuit to a particular frequency so that you get the maximum power out, and this is the specific frequency that you would have to tune it to. So why do we care about this? Why are we worried about this special resonance circuit? Well, perhaps you have a circuit and you have some supply that's coming in, and the best example I can think about is an older radio, not so much the digital radios, but an older radio which has a response, right? So if you were going to tune your radio to a particular channel, those channels are in hertz, and so you want to match the frequency from the radio station to the frequency of your particular radio receiver, and you want to be able to pick up that particular channel. So our goal would be to have certain power from radio stations pass into our circuit and be able to pick them up, while others do not get picked up for that particular frequency. So we have this idea of a response where frequencies in a particular range would pass and be picked up by our circuit, and all others would be rejected. And so in a perfect world, we would have some, here would be our frequency, our resonance frequency, and then we would have a range a lower frequency and a higher frequency, and anything in that range we would pick up in our circuit and we would have the same amount of power. This is an ideal frequency response curve. And so F sub r is our carrier frequency, and it's also our resonance frequency. So the idea is that the radio station out there has some carrier frequency that it's sending its signals out, and we want our circuit to be able to pick up that particular frequency and have a maximum power transfer at that resonance frequency. And we notice that we have this thing called BW, that's the bandwidth, right? So that means that anything in our frequency range from F1 up to F2 would pick up in our circuit. And so when we're adjusting our radio station, right, we have a little bit of a range there where we could pick up those values. This is a perfect response curve, right? But in an ideal world in our circuit, the power actually is not a flat curve like this. We have some maximum power, and that maximum of power occurs at resonance, and then the curve sort of flattens off on either side. So we define our bandwidth for a real response curve as having some lower frequency and some upper frequency, and our circuit will pick up those frequencies as long as the power here is half of the maximum power, and then anything that's half of the maximum power below that, it'll cut off. So it still allows us to have some bandwidth or some adjustability in tuning our radio to a particular frequency. And this is just one example. There's obviously other examples that we could have in terms of using a resonance circuit, but the radio example is something that we're all somewhat familiar with. So let's focus on looking at, how do we define this bandwidth and so on. Okay, before we do that though, let's just look at this simple circuit, and we want to find the voltage across each of the components when this circuit is set up for resonance. So when this frequency is set up to actually have resonance. So we know that the total impedance in the circuit at resonance will all be resistive because the reactive components have canceled each other out due to this frequency being set at just the right value. I can then determine the total current in the circuit, and the current is just the voltage divided by the total impedance, which is all resistive. Again, these two components have canceled each other out at resonance. And so the total current is just the voltage supply over the resistance, and it has, in this example, a phase angle of 0 because my source is 0. I can then determine what is the voltage across each of the components. So the voltage across the resistor would be the current times the resistance. And of course, that's just going to be the source because that's how we started our whole discussion, with the fact that this resistor at resonance gets all of the voltage of the source because those two components cancel in terms of their voltage. The voltage across the inductor would be the current times the inductive reactance with a phase angle of 90. And then the capacitor would be the current times the capacitive reactance, and then the phase angle here is minus 90, so I get a negative 90 here. So keeping in mind that the reactive components for the inductor and the capacitor are exactly equal to one another, the values for these voltages are actually the same, but they are out of phase by 180 degrees, which basically means when one is positive, the other one is negative, and they have exactly the same value. Right, so these two are exactly the same. So at any given time, the voltage across the inductor will cancel out the voltage across the capacitor, and the resistor gets all of this voltage from the source. That doesn't mean that there isn't voltage across these components. There is voltage, it's just that it's actually equal and opposite. And so in terms of Kirchhoff's voltage law, if you sum the voltages around the loop, the voltage across this inductor will exactly cancel the voltage across this capacitor, and so the resistor actually gets all of that source voltage. So at resonance, The average power in the circuit is just the current squared times resistance, where this current is the maximum amount of current. There is still reactive power dissipated by the inductor and the capacitor, and so the reactive powers I could certainly figure out. For each one, it would be the current squared times the reactance. And again, this is just the amplitudes, right? These are not phasors, these are just the amplitudes of each of those values. But the reactive powers are equal and opposite. So if I add the total amount of reactive power in the circuit, I would have positive reactive power for the inductor, negative reactive power for the capacitor. And so if I wanted to know what the apparent power in the circuit is, it's just the square root of the real power squared plus the reactive power. But adding those two reactive powers together they'd cancel out, and so there is a total of 0 reactive power, and so the apparent power in this particular circuit for resonance is all real power. So I just want to sort of reiterate that even though those components are canceling each other out, that doesn't mean that there isn't still voltage across those components, and that voltage can actually be relatively large. And it doesn't mean that, that there isn't reactive power as well, but again, those things are canceling each other out. So one of the things that we define for a resonant circuit is something called the quality factor, and so we're looking at this specifically for series. Unfortunately, the symbol that's used for the quality factor is also a Q, similar to reactive power. So what I have done is I have gone ahead and put a subscript of factor on the Q so that we know that we're talking about the quality factor. So the quality factor is a measure of what the reactive power in the circuit is compared to the average power. And so since the reactive power can be from, so I have to be more specific. So it's the reactive power for either component. So how does the reactive power across the inductor compare to the real power in the circuit? Because obviously the total amount of reactive power in the circuit is 0. So this quality factor is actually measuring the reactive power of the inductor or the capacitor compared to the total average power in the circuit. So the quality factor is this reactive power over the total power. And so the reactive power can be written as the current squared times the reactance. The real power is the current squared times the resistance. This reactance can be inductive or capacitance. We usually choose the inductance part, but certainly we could do the capacitor part. The currents here are just the amplitude of the current in this series circuit, so they cancel each other out. And I get that the quality factor in a series circuit is just the inductive reactance, the ratio of the inductive reactance to the resistance in the circuit. And I can write down what the inductive reactance is. It's the angular frequency times the inductance. So we have this quality factor, which is going to be just a number. It doesn't have any units associated with it. And it's going to tell us how big is the reactive power in the circuit for the inductor or the capacitor. How big is that compared to the real power in the circuit? So if you get a number that's bigger than 1, that means that that reactive power from those components is bigger than the real power, and if it's less than 1, then it would be smaller. So that quality factor is often bigger than 1, and it's often a large value. So that just means that that reactive power is relatively large in the circuit. The voltage across the inductor and the capacitor can also be larger than the source. So that's another possibility that can occur, is that you have a certain voltage supply and the resistor is getting all of that voltage, but that doesn't mean that current isn't flowing through the inductor and the capacitor. And so the voltage across those other components, those reactive components, can actually be larger than the source because, again, they're canceling each other out. So if I go back and I write down the quality factor as I have it above, so the reactive power over the real power, and I just divide one of those currents out, then I have that this is the current times the reactance of the inductor or the capacitor, doesn't matter which one, over the current times the resistance. The current times the resistance is the voltage of the source, and the top current times reactance is the voltage across the inductor or the capacitor, depending on which one we're talking about. And so essentially this quality factor, this number, is telling us what is the maximum voltage across the inductor or the capacitor compared to the source. So if your quality factor was 10, that means that the maximum voltage across the inductor and the capacitor is 10 times the voltage of the maximum voltage of the source. So the quality factor is actually kind of a nice thing to know, because it's going to tell you how big of voltages you're getting across those reactive components. So let's look at just a quick example here. So we have a circuit on the left. It has some voltage supply. There is some resistor in the circuit, capacitor, there's an inductor. And then because this is sort of all shaded here in blue, there's also some resistance of the coil. So the inductor is just a wire, of course, that's wrapped around a number of times, and that wire has some resistance associated with it. So a real inductor is often written as an inductance in series with whatever the resistance of the coil is. So we want to determine what the resonance frequency is and what the resonance angular frequency is also. So we know that the resonance angular frequency is just 1 over the square root of the inductance times the capacitance. I need to make sure that I have these values in terms of the standard units. So my inductance I would convert to Henry, so 10 millihenry is 0.01 Henry, and my capacitance is 1 microfarad, which is 1 times 10 to the minus 6. So this ends up giving me an angular frequency for resonance of 10,000 rads per second. Once I know what the angular frequency is for resonance, I can calculate what the frequency is in hertz by taking my number and dividing by 2 pi, and I get 1,591.5 hertz. I can also determine what the total impedance in the circuit is at resonance. And I know that at resonance that the reactance of the inductor and the capacitor cancel each other out. So the total impedance is just the total resistance in the circuit. But I don't know what the resistance of this coil is right here, right? It's not given to me. But you'll notice that I have this Q coil. This is called the quality factor of the coil. And so I can determine what the resistance of the coil is based on this quality factor. So in general, the quality factor, and I didn't put Q factor here, but the quality factor for the coil can be written as the angular frequency times the inductance over the resistance. And so I can solve for the resistance of the coil based on this information that I have and the resonance frequency that I found here. So if I cross multiply, I get that the resistance is just the angular frequency times the inductance over the quality factor for the coil. So my resonance frequency was 10,000, my inductance is 0.01, and my quality factor for the coil was 50. So if I put all those values in, I end up getting 2 ohms for the resistance of the coil, which means that my total resistance in the circuit would be 8 ohms plus 2 ohms, which gives me 10 ohms. I can also determine what the current is at resonance, so I have some current in this circuit, and so the current is just the voltage over the impedance. The voltage is 10 volts, phase angle of 0. My total impedance is all resistive because I'm at resonance, and so this is just 1 amp with an angle of 0 degrees. Knowing what the current is in the circuit, I can go back and I can figure out what the voltage is across the inductor and the capacitor. So the voltage across the inductor is just the current in the circuit times the impedance of the inductor, and the voltage across the capacitor is the current times the impedance of the capacitor. I need to be able to write down what those impedance values are. So at resonance, the inductive reactance is the angular frequency times the inductance. So 10,000 times 0.01 is 100 ohms. And the same thing for the capacitor, 1 over the angular frequency times the capacitance, I get 100 ohms. So I know that these two should be equal to one another because we're talking about resonance, and that's how we define resonance, is that the reactive values are exactly the same. So once I know what the reactive component is, I can find the voltage is the current times the impedance of the inductor has a phase angle of 90. So it's 100 volts with a phase angle of 90. And I can do the same thing for the capacitor. It's the current times the impedance of the capacitor, which has a phase angle of minus 90. So it's 100 volts, phase angle of minus 90. So this is an example where the voltage of the source is 10 volts. The resistor, total equivalent resistance here, gets that 10 volts. But even though the voltages across the capacitor and the inductor cancel each other out because they're 180 degrees out of phase, they still have a large voltage, right? They both have 100 volts on them, which is much larger, right, than the source. We can also calculate what the real power and the reactive powers are. So the real power would be the current squared times the resistance. That's a maximum current of 1 amp times 10 ohms, which would be 100 watts. And then the reactive power for the inductor and the capacitor would be the current squared times the reactance, which would be 1 squared times 100, which is 100 VAR. I want to point out here, and I wasn't real careful with this, is that these are the magnitudes only. So the reactive power for the inductor would be a positive 100 VAR, and the reactive power for the capacitor would be a negative 100 VAR. And so when you add those two together, the total reactive power in the circuit is just 0. So we could also calculate the quality factor and see if everything sort of makes sense according to this quality factor that we've defined earlier. So the quality factor is just the angular frequency times the inductance over the resistance. So 10,000 rads per second times the inductance over the total resistance, and I get a quality factor of 10. So remember, the quality factor was important because it told us how the voltages compare with one another, right? So the voltage across the inductor and the capacitor should be just the quality factor times the maximum voltage of the source. So the quality factor was 10, the voltage was 10 of the source, and I got 100 volts. And that matches what I got for the voltage across the capacitor and the inductor. So that quality factor is really telling us quite a lot about the circuit. It's telling us, how those voltages across those reactive components at resonance compare to what the source is. It's also going to tell us how the powers compare with one another. If I take the reactive power of 100 VAR, right? So the quality factor is also defined as the reactive power over the real power. So 10 VAR over 100 VAR over 10 watts is also 10, right? So that also is giving us the correct value here, and it's telling us that the reactive power is going to be 10 times larger than the real power. So one of the things that we can look at in terms of a series resonance circuit is what the impedance looks like. And so we talked about the fact that in a series resonance circuit, the resonance occurs when the impedance is a minimum. And so here is a graph of what the impedance looks like for a given circuit versus the angular frequency. And so here is my resonance angular frequency. My impedance is the smallest value possible when all of the impedance in the circuit is just resistive, right? And that's that right there. Then what happens is that when the angular frequency becomes larger than the resonance frequency, that would be going to the right. If I look at my total impedance in the circuit, my total impedance is the resistive piece plus the reactive pieces. So I have the inductive reactance here, and I have the capacitive reactance over here. So as the angular frequency gets larger, that means that the term for the reactive inductance, this piece here, as the angular frequency gets bigger, this term is going to be larger than 1 over the angular frequency times the capacitance. So basically, as the angular frequency increases, the inductive impedance dominates, right? This piece is going to dominate. On the other hand, if you are at series resonance and you decrease the frequency, so now the angular frequency becomes less, this number becomes smaller, and as the angular frequency decreases, this whole number here, the capacitive reactance, increases, and so capacitive impedance dominates. But the curve has, sort of the impedance has this curve associated with it, right? And so we could actually write the total equivalent impedance by putting the reactive pieces over a common denominator of angular frequency times capacitance. So I multiply the term here by angular frequency and capacitance. I get angular frequency squared times the inductance times the capacitance. And then if I wanted to, I could convert this, which is in rectangular form, into polar form by squaring the real part and squaring the imaginary part. And I get the total equivalent impedance is just the resistance squared plus this term here squared as well. And that's how we get this curve here that looks like something that depends on, you know, x squared plus y squared and so on, right? So it's got this polynomial type of squared curve associated with it. Or, you know, it looks like a square root with terms that are squared in it. We can also look at what the phase angle will be for our impedance. And so as we increase the angular frequency, right, same picture as above, we increase the angular frequency, our phase angle for our impedance should be positive, right, because the inductive impedance is dominating. And then if we decrease the angular frequency, then the capacitive components are dominating. And so the phase angle should be negative. And that actually naturally comes out from this expression right here. But I think it just makes sense by looking at our picture in terms of which is dominating, because inductive reactance has positive phase angles and capacitive reactance has, the capacitive impedance has negative phase angles. But this expression for the current is basically just using what we know about converting polar, rectangular to polar. So we take the tangent inverse of the imaginary part divided by the real part, and that's how we get this component right here, and that's why that resistance is on the bottom, because we've taken that term and divided by the resistance. So obviously the power is going to change as the frequency changes, because what happens is that from the last picture that we had, when we're at resonance, we have the lowest amount of impedance in the circuit. And then as we increase or decrease the frequency, the impedance changes. It's not a linear relationship, right? It's got this curve associated with it. And so what's going to happen is that I'm going to get a power that's not constant. So at resonance frequency, the power is a maximum, and we know the power is a maximum and the current is a maximum because of the fact that we have only resistance in the circuit and the impedance is a minimum. But then it drops off as the frequency decreases and as the frequency increases, because the impedance has changed. So at resonance, the power is going to be a maximum. as the angular frequency approaches 0, so as I go to the left over here, what's happening is you're not getting a fluctuation any longer. As the angular frequency goes to 0, you're not getting any sort of fluctuation anymore in the circuit, and so that means that the capacitor is behaving as an open circuit because it's fully charged, and capacitors behave as open circuits when they're fully charged. And so so this part of the circuit over here, you're sort of reaching a point where the current is sort of steadying out at that point in the circuit. And then of course on the other side, when the angular frequency increases, this is where the inductor is sort of dominating, and if you have a really large fluctuation, what's happening is that the inductor is behaving as an open circuit because of the fact that the inductor, remember, doesn't like change, and if you have something that's fluctuating extremely quickly, the inductor is going to resist that and produce a voltage to oppose that change. And so on the opposite side, the inductor is starting, as it goes to infinity, is starting to behave as an open circuit.